The ideal gas law. There is no such thing called as an ideal gas in the real world. It's purely hypothetical. However, real gases could behave ideally at high temperatures and low pressures. So what is the ideal gas law? Well, basically chemists came up with this expression, PV equals nRT. Right. So before we try to understand this equation, let's see what an ideal gas is. Let's say if I have an ideal gas in a container, the gas is said to be ideal when the particles take up almost zero space. The volume taken up by these ideal gas particles is almost zero. That's one. Secondly, these particles have almost no intermolecular force of attractions. They don't attract each other. For example, if I have an ideal gas particle trying to go and collide or hit with the walls of this container, let's say I have this particle trying to go and hit with the walls of the container. The other particles just sit back and watch. They don't attract this particle. They don't try to pull it down. So they're pretty nice to each other. Right, so that's an ideal gas. The particles take up almost zero volume and there is no intermolecular force of attraction. Now let's try to understand what this ideal gas equation is. So you have four variables: pressure, volume, number of moles of a gas, and temperature. And we'll try to understand what R is. So to understand that, let's start with some of the basic gas laws. So we have the Boyle's law, which says pressure is inversely proportional to volume. In other words, when you increase the pressure, the volume decreases. Think about the bicycle pump. When you apply more pressure on the piston, the volume of gas inside the pump will be smaller. So if I rearrange that, that would be PV equals to constant. Then you have Charles' law, which says that volume is proportionate to temperature. You increase the temperature, the gas particles gain more kinetic energy and they take up more space, so the volume increases. In other words, volume over temperature is a constant. Then you have Gay-Lussac's law, which says that pressure and temperature are directly proportionate, which means when you increase the temperature, the particles have greater kinetic energy, so they're going to collide more frequently with the walls of the container. So more collisions mean more force being applied on the walls of the containers, so the pressure increases. In other words, pressure over temperature equals to constant. Then finally we have Avogadro's law, which says that volume of a gas is proportionate to its amount, or the number of moles. When you have more volumes of gas, of course there are more particles, they're going to take up more space. So if you rearrange that, that would be V over N equals to constant. So if you basically combine these four expressions for the four gas laws and look for some commonalities. So in the numerator I have pressure and volume. I don't think there is any other variable. And then in the denominator I have N, which is the number of moles, and temperature. That equals to a constant, and this constant is called the universal gas constant, represented by capital R. And one of the most important things about this expression is you need to be really careful with the unit system. So let's talk about the unit system below. How to plug in the right units when you apply this formula and do problems. So in the SI unit system, let's say I'm applying the SI unit system. So pressure is usually in Pascal or kilopascal. Pressure is usually in Pascal or kilopascal. And the unit of volume, the SI unit of volume, is usually meter cube. It's not decimeter cube. The SI unit of volume is meter cubed. Of course, N is just number of moles. There's no conversion factor for that. And N is moles. It's not really an SI unit. Temperature is always in Kelvin. So your pressure is in Pascal or kilopascal, that is the SI unit, and then your volume is in meter cubed, N is in number of moles, and temperature is in Kelvin. That's just 1L. So in the SI unit system, usually R has a value of 8.31 joule per Kelvin mole. That is the SI unit of the gas constant. However, if you're applying, alternatively you can apply a different unit system for the same expression. So in the other unit system, if you can have pressure in atmospheres, you can have volume in liters or dm cubed, and of course N doesn't change, that's just moles, and then you have temperature is always in Kelvin. So when you're applying this unit system, usually your R value is 0.0821 liter atmosphere per Kelvin mole. So there are two unit systems that you can apply to solve problems based on the ideal gas equation. You could use the SI unit system where the pressure is in Pascal or kilopascal, volume is in meter cubed, temperature is in Kelvin, N is always moles. Or you can use the other system where pressure is in atmospheres and volume is in dm cubed or liters, and temperature is of course in Kelvin. So then your gas constant is going to be 0.0821 liter atmosphere for Kelvin mole. So it's really important to use the right units when you plug into this expression, otherwise you're going to end up with values or results that would be way off from the actual value. So that concludes the video on the ideal gas law, also known as the ideal gas equation.